This is problem 3-6. Part A says, in terms of the constants A and B, determine the following. The position R0 at which the potential energy is at a minimum. So the formula you're given for potential is A times R over B plus B over R. Now you're going to take the derivative of this, du over dr, and you end up getting AB over R squared minus A over B. And this is R naught. And basically what you're going to do then is you're going to set it equal to 0 because you want to solve for the minimum. So where slope basically changes, which is solving for 0. And you're going to bring this over on the other side, so A over B equals AB over R naught squared. Then A's cancel out. And then R naught squared equals B squared, square root, R naught equals B is where the minimum is going to be. Then the minimum potential energy U naught, you're just going to plug it in, U of B, which is going to be A times B over B plus B over B, which is just going to be 2A essentially, both equal 1. Then for the next part it says, sketch the net force of the particle as a function of r on the graph below. And basically it says the force directed toward the origin is negative, away to be positive. Now based on this graph you can tell at r naught the force is going to have to change from positive to negative. So you're also given in the same spot is when force equals negative du over dr. In part A, you basically had to solve for the derivative, so you already have AB over R squared minus A over B. So force is just going to be negative AB over R squared plus A over B. So you're just going to graph it based on this. So here's your force, 0, and it's going to just look like a concave down graph with this being R naught. Now it needs to be concave, it's concave up. Concave up here, it needs to be sloping down like this and needs to intersect at R naught. And then it says the particle is released from rest at R equals R naught over 2. So in terms of U naught and M, determine the speed of the particle when it is at R equals R naught. So we're basically just going to use energy equals kinetic plus potential. You know when it starts off it has no kinetic energy, so you can just write U of R naught over 2. And now you want to solve for when it's at R naught, so it's going to be equals U of R naught plus the kinetic energy, 1/2 mv squared. You know this from solving earlier, this is just going to be 2A. And this one right here you can just plug into the formula, which I'm not going to do the work, too much canceling out and all that stuff. But essentially in the end you're just going to end up with, I believe, 5A over 2 is what you get for the potential at R naught over 2. So 5A over 2 equals 2A plus 1/2 mv squared. So then you're going to subtract 2a, so a over 2 equals 1/2 mv squared. These cancel out. You're going to end up with a over m equals v squared. V equals square root of a over m. And you can't leave that a in there, you need to replace it with u naught. And you know u naught equals 2a, so you're going to end up with v equals square root of u naught over 2m to cancel that out. So your final answer is v equals square root of u naught over 2m. And then write the equation that could be used to determine if the particle will again come to rest. It's not necessary to solve for this problem. You can simply just set u of r whatever. You can call this rx, r1, r any numeral, I'll just call it rx, equals u of r naught over 2. Basically when the potential equals the other potential when it's at rest. It's going to basically be at rest again because conservation of energy. That's all you need to write for that problem. You don't need to write anything else, you don't need to solve it. Now the last problem. Briefly and quantitatively describe the motion of the particle over a long period of time. So it's going to be oscillating because the potential energy is basically fluctuating over time, kinetic energy fluctuating with it, which basically gives it no choice but to oscillate. So it's going to oscillate, and then basically when the potential equals initial, or basically when it equals Rx, which is what you quantified in the last one, or initial u naught, it's going to be at rest. And then when u naught is at a minimum, basically kinetic is at a maximum. Etc. and so forth. You're basically just describing the motion of the particle, how it's just going to basically be repeating itself. And that pretty much wraps up this problem.